Today we're going to look at the graphs of what are called the sinusoids, or the graphs of sine and cosine. We went pretty in depth with these graphs in Algebra 2 and in Honors Math 4. Now we're going to kind of scratch the surface with them again, but then talk about their transformations and then applications with them and how to model with these graphs. So we're going to start with the connection between these graphs of y equals the sine of x and y equals cosine of x in the unit circle. So I'm going to start by putting the quadrantal angles on the unit circle here: 0, pi over 2, pi, 3 pi over 2, and then obviously what is also 2 pi here. We'll just keep it at 0 though, but it is the same. They are coterminal angles. So the values of cosine and sine at the quadrantal angles are the x and y values on the unit circle. And we're also going to label the sine and cosine values of pi over 4, because that's going to help us to fill out these two tables here. So the first angle that we're going to have is the angle pi over 4, and then we'll have 3 pi over 4 in the second quadrant, 5 pi over 4, and 7 pi over 4. The sine and cosine of these angles is the y and x values on the unit circle respectively. So we know from our special right triangles that the sine and cosine of both of these, or of all these, I should say both the sine and cosine of pi over 4 and all of its angles that have it as a reference angle, are square root of 2 over 2. So these are the values that we're going to have throughout the unit circle, except we know that in some cases it's going to be negative. In the second quadrant, we know we are negative cosine. In the fourth quadrant, both cosine and sine are negative. And in the it's the third quadrant. Say negative, negative. And then in the fourth quadrant, we are positive cosine, negative sine. So we're going to use these values to help us fill out these two tables here by taking some trips around the unit circle. So we want all of our quadrantal angles. I'm going to zoom out so we can see the unit circle at the same time. We want all of our quadrantal angles will end up being either 0 or 1, or negative 1. So starting at 0, we're going to look at the sine graph first. So we're just looking at all the y values over here for right now. So right now we're focused on just these y values as we take a trip around the unit circle. All right, those are going to end up being the values in our table over here. So at 0, the sine value is 0. I'm going to do all the quadrantals first. At pi over 2, it's 1. At pi, it's negative 1. 0. 3 pi over 2, it's negative 1. And then 2 pi's coterminal is 0. Now we'll do the angles that have pi over 4, or 45 degrees, as a reference angle. In the first quadrant, pi over 4 has a sine value of square root of 2 over 2. The sine of 3 pi over 4 is also the square root of 2 over 2. And then we are negative in the third quadrant and in the fourth quadrant. When we get to 9 pi over 4, we really are in these two columns, just repeating what these two columns are. When we're at 9 pi over 4, we're back into the first quadrant, so we have positive square root of 2 over 2. So as we look at the graph of y equals the sine of x, it's already there. So none of these values are really a surprise to us. But what I want to do is kind of connect some things in the graph. For example, that value square root of 2 over 2, that's about 0.707. So what we're going to do is we're just going to put a light line at about 0.7 going across the graph, and at negative 0.7. Just to show that when we split this graph into fourths here, Here we have pi, here we have pi over 2, here we have 3 pi over 2, and we have 2 pi. We would have all of our quadrantal angles labeled. At pi over 2 we have 1. At 3 pi over 2 we have -1. At 0 we have 0, and at 2 pi we also have 0. But when we put that line square root of 2 over 2 on the graph and negative square root of 2 over 2, we can see why the graph has points where it does, because we intersect the graph right at those points. There's pi over 4 right there, and 3 pi over 4, so that's the first and second quadrant. Now we're in the third and then the fourth quadrants with those values. All right, we're not going to put those lines in this graph just to speed things up a little bit, but we are going to put the values in for cosine. At 0, cosine is 1, so now we'll take a look at all of the green highlighted values for cosine. So at 0, we know the cosine is 1, and that's why we started our maximum. Pi over 4, we're square root of 2 over 2. Pi over 2, 0. 2 pi over 4, we're negative square root of 2 over 2. So that's why we, that's why we are down here. At pi, we're at -1. Put some of these on here as we go. At 5 pi over 4, we're still in the negative square root of 2 over 2. 3 pi over 2, we're at 0. 7 pi over 4, we have square root of 2 over 2. And now again, we're back to a coterminal angle with the x-axis, or with 0, and that's 2 pi. So we have a value of 1. We're back at our maximum. And then at 9 pi over 4, we're at square root of 2 over 2. And the pattern continues. These are called periodic functions. These are functions that repeat the same y values for a consistent interval of x values. And a sinusoid is any function that can be written in the form y equals a times the sine of bx plus c plus d. And this is kind of relative. Okay, what we're going to do most of the time is, instead of leaving it in that form, we're going to put it in that form. And C is not meant to represent the same thing in both those forms, because if it did, then this one would actually say C over B. This is just giving two different forms. They just happen to use the same letters in each. We will usually try to get ours into this form here, where the B value is pulled out, because B helps us find the period. The A value, in either case, A, and I've bolded it here, gives you the amplitude. Whatever the absolute value of A is the amplitude. Graphically, the amplitude is the half of the height of the wave, or the distance from the midline, which in our case in those two graphs already was the x-axis, to the maximum, or to the minimum. The period of both of these functions that we've graphed so far, you probably remember from Algebra 2, this is considered to be one cycle. That's one cycle right there. Okay? The length of a cycle is one period. That's called a cycle. But the length of that cycle is called a period. And of both of these functions, the period is 2 pi. However, if you have a value in the sinusoid function where this b value is something other than 1, then we find the period by taking 2 pi over b. It's actually 2 pi over the absolute value of b. Graphically, the period is the length of one full cycle of the wave. Another thing that b tells us, b is the number of cycles from the interval 0 to 2 pi. So when b is 1, the period is 2 pi, because you can fit one cycle from 0 to 2 pi. All right, in our first example here, we're going to describe the amplitude in each of these graphs. In the first graph, we already have, oops, I have the period listed there. Let me get rid of that. The amplitude is 1, okay, unless if there's an A value there. If you see nothing there, the amplitude is 1. And that means that the graph is going to oscillate between minimum values of -1 and maximum values of +1. Here our amplitude is 1/2. And here our amplitude is 3, and we'll talk about that negative in a second, because the rest of the directions say to use the language of transformations to describe how the graphs are related. So what we're going to do is compare the functions in B and C to the function in A, that parent function y equals the cosine of x. So in B, we would say that this is vertically shrunk by 1/2. And in C, it's vertically stretched by 3. And it's also reflected, because of the negative, over the x-axis or over the midline. I'll just put over the x-axis, or it's reflected vertically. Remember, anything that happens on the outside of the function is a vertical transformation. So reflected vertically, stretched vertically. Okay, this one shrunk vertically. And what's on the outside does exactly what it looks like. If that's 1/2, it's going to shrink it by 1/2. If that's 3, it's going to stretch it by 3. On the inside, however, it does the opposite. All right, and that's going to be related to the period. So in the next set here, we're looking for what the period is, and then we're going to use the language of transformations again. In this first one here, B is 1, so the period is just 2 pi. In this next problem here, it's important to identify that B is 1/3, because that basically says 1/3 x there. Since B is 1/3, the period is going to be 2 pi over the absolute value of 1/3, or 2 pi times 3, which is 6 pi. So the period is 6 pi. And if you think about how many cycles you'd be able to fit from 0 to 2 pi, then, if the period is 6 pi, this is oops, we're 6 pi, and this is the whole period. How many cycles would be able to fit between 0 and 2 pi would be 1/3 of a cycle, which matches with our definition that B is the number of cycles between 0 and 2 pi. So that's the period. It doesn't say anything about the amplitude in example 2, but let's talk about that anyways. The amplitude here is 2. And then when we compare it to the parent function y equals the sine of x, we know we are stretched vertically by 2, reflected vertically because of the negative, reflected over the x-axis. And now remember, on the inside it does the opposite. So since it's a 1/3, it's actually a stretch by its reciprocal 3. And stretched horizontally by 3. In our next example here, we have an amplitude of 3. The period is found by taking 2 pi over the absolute value of -2, which is just going to be pi. B is 2 in this case. Actually, B is -2. The negative means that we're going to flip it, and the absolute value of -2 is going to help us in finding the period, which it just did. But what we're going to say in our transformations is it's going to be stretched vertically. Take care of that amplitude first. Stretch vertically by 3. Vertically by 3. Horizontally. Now this time it's going to be shrunk by 1/2, which looks weird with the 2 right there, but if you think what you just wrote about the period being pi, we're clearly saying that it's half of what the parent function normally is, 2 pi. So it's horizontally shrunk by 1/2, and it's reflected horizontally because of the negative b value. So it'd be reflected over the y-axis. All right, so let's put this to use here and graph a few trig functions here. We're not going to get as detailed with these as we did in Algebra 2. We're just going to basically, and we're not going to be to scale as much as we were. We're going to try a little bit to keep this to scale. But sometimes we're just going to be worried about trying to find where the mins and maxes are, where the x-intercepts are. So we can just use a non-scaled sketch to help us with that. So in our first one here, we have an amplitude of 2. So I want to go up to 2 on the y-axis and down to negative 2 on the y-axis for my max and min. So I'm going to put 2 here. And then I'm going to put negative 2 here. And then I'm going to put, because the period is 2 pi, what I want to do is go out on the x-axis to 2 pi, and I like to use multiples of 8 if I can for this, or at the very least a multiple of 4. What I mean by that is I want to go up by 8 lines, or if I had a much bigger, more detailed graph, I try to go like 16 or 32 lines, because I can easily split that up to give me a nice trig function. I'm going to go 8 units to 2 pi here, and then I'm going to cut that in half and label it pi. I'm going to cut that in half and label it pi over 2. Now we want to find this value right here, which obviously we know in this case, but the easiest way to get that value right there is to multiply this guy by 3 to figure out what that's going to be. So this is going to be 3 pi over 2, because you have 1, 2, 3 of those to get to that spot. So that's 3 pi over 2, which is pretty easy to get in this case, but if this number were uglier, then that'd be a nice trick to use. Okay, so we're going to go ahead and graph this here. It is a sine function. Sine functions start at the point 0, 0. If it is a positive a value, it's going to start by going up and then coming back through and then ending at the x-axis as well. So it's going to go up and come back through halfway. So I know I've got those 3 points to start with. Because it goes up to start with, I know my maximum is going to happen 1/4 of the way, and my minimum is going to happen 3/4 of the way through the cycle. And that basically is as much as we're going to use most of the time here. For one of these problems, this relates to what we did in Algebra 2, though. I am going to put those points that were halfway in between these 4th values, or the 8th points, call them all sorts of different things. So they'd be at the values of pi over 4 and its multiples, its odd multiples. They will be, normally they are square root of 2, right? But since this whole thing got multiplied by 2, we want those at 2 square roots of 2. Actually, I said that wrong. They're usually at the square root of 2 over 2, which is the 0.707. Now we're going to have them at 2 times that, or 2 square roots of 2 over 2, which is just the square root of 2. Square root of 2 is about 1.4, which makes sense because we were at 0.7 before. So at about 1.4, which is about right there, I'm just going to make that light blue line again. And I'm going to use that to help me graph just a few more points in this case. We won't always do this, but I think since we did it so much in Algebra 2, this isn't a bad idea. So I know I'm going to have a point here and here, here and here. Everything got stretched vertically by 2 because of that a value. All right, and then here's what our graph looks like. I'm going to draw it going through these points and make it look like it doesn't just start and then stop. We are just simply drawing one cycle of this graph, but it goes on forever in each direction. Okay, the domain is all real numbers. The range is all real numbers between -2 and 2 inclusive. Okay, for the rest of these, we won't put those 8th points in. We'll just split it into 4ths. So the next one has an amplitude of 1 because there's no a value, or there's an a value of just 1. And I'm going to keep with my same colors there. So the amplitude in this one is 1. The period is going to be 2 pi over 2, or pi. And we're going to get 2 cycles between 0 and 2 pi. I'm going to throw an x and a y axis in here. And then I'm going to put my value of 1 right there. And my period of pi, I'm going to go 8 again, but this time I'm just going to split it into fourths. So we got pi over 2, pi over 4, which would be 1, 2, 3 pi over 4 right here. And then we've got our max and our mins. And if you want to use lines to help you with that too, sometimes this helps from us making mistakes about where the max and mins are. I didn't do that in the last one because I already had those blue lines on there, but now I can put my my points on here. This is a cosine graph now. Cosine will always start at the maximum value as long as a is positive. So we're going to start here at 1. The cosine graph then will end at its maximum in that cycle. Okay, it keeps going obviously after that, but for that cycle, that's where it's going to end. And then halfway through, it'll be at its minimum. So I have those 3 points there. Well, that pretty much leads us to see that we have to get through those 2 points there. And then when you graph this, make sure that you treat your maximums like maximums here. We don't want to have our arrows going through the graph like that. Those are maximums. Okay, 2 more graphs here. We've got one now that's going to have a negative a value, which means we're going to reflect vertically over the x-axis. Okay, our b value is 1/2, so the period is going to be 2 pi over 1/2, which is 4 pi. And our amplitude is still 1, it's just that we're going to reflect. Okay, so we've got y. Let's make sure to make my axes here. There we go. All right, so we've got a period of 4 pi. And 4 pi, that's obviously over 12. So I'm going to kind of keep that into consideration as I'm putting my values on my y-axis. My amplitude is 1, so I don't want to put my my amplitude way up here and say that that's 1 because that's really off scale. I would say either the first or the second. At least it looks like you're trying to keep it somewhat to scale here. Okay, so now this is a negative cosine. Cosine will normally look like this. Oops, sorry about that. Cosine will normally look like this. There we go. But because it's reflected, we know it's going to start down at its minimum, hit its maximum halfway through, and at the end of the cycle, end up at its minimum again. So we need to go through the x-axis in the same points. That doesn't change. This is what our graph is going to look like here because of the reflection. Okay, we've got a graph here that we're not going to be able to scale very well at all. Do our best. You'll see why in a second here. The amplitude is 1/3, so obviously that's very small. The period, because b is 1/4, is going to be 2 pi over 1/4, or 8 pi, which is over 24. I'm going to come out here to 8 pi, and then split that in half, multiply that by 3. So since my amplitude is only 1/3, I'm going to put that value there and try to make this as close to scaled as possible while leaving these the nice grid lines, cutting it by eighths and using the grid lines that I'm given in order to make this a somewhat decent looking graph. So we've got a sine graph now. It's not reflective. So we're going to start at the origin. If it were a negative a value, we would go down from that point. So my next point would be here, and then here, and then here, and then here, if it were reflected. But it's not. So we want to, from the point 0, 0, we're going to be going up. So 1/4 of the way through, we hit our maximum, come back down through the midline, then we hit our minimum, and then we're back at the midline again. There's our graph. There's lots of other things that can happen. Hopefully these 4 graphs give you an idea of some of the things that we'll see. Because we're also going to be translating these as well. We'll get there in the next video. Okay, the last thing that we're going to touch on in this video here, last 2 things. The first is pretty straightforward. It's what frequency is, and we've actually kind of used this terminology before. We've just never called it frequency. Frequency is a way to tell the number of cycles that we'll have in a unit interval. It's the reciprocal of the period. And we've kind of used it when we've been saying that B tells us the number of cycles that we can fit from 0 to 2 pi. It's kind of a step into what the frequency is telling us. So let's take a look at this next function here. Y equals 4 sine 2x over 3. The B value in this is 2/3. So the period, let's find the period first here, since we've done that before, is 2 pi over 2/3, which is 2 pi times 3 over 2, which is 3 pi. That's the period. All the reciprocal is the reciprocal, or excuse me, all the frequency is the reciprocal. The frequency is 1 over 3 pi and tells us there is 1 cycle every 3 pi units. That's what their frequency tells us. It's just another way of describing what the period is. And we'll use it in interpreting some of these functions in more applicable senses. All right, now we're going to talk about the translations. I guess we are going to get to this in this video a little bit here. This is something that we talked about earlier on in this class too, in section, I believe it was 1.5. We've got vertical stretches, vertical shifts, horizontal stretches, and horizontal shifts. The way that it's written here with this being positive is a little bit different than what we've done in the past, because normally we say C or H, we've had in here before, does the opposite. In fact, if you want to write our old friend from Otter's Algebra 2, y equals a times the sine, and I'm just going to put this, group this a little bit differently, b times x minus h plus k. This is kind of what we're used to. It doesn't matter which form you want to use. Everything means the same thing. It's just you got to interpret it correctly. We are doing the opposite on the inside now. So if that's a number bigger than 1, we're actually shrinking. If that's a number bigger than 1, we are stretching because it's on the outside. If this is a positive value, we're actually going to go to the, well, let me say it this way. If this says minus in here, we're going to the right. And if that says plus, we're going to the left, just like our other translations. And we're doing the same thing as we always do here. If it's positive, it goes up. If it's negative, we're going down. So one thing that we want to make note of here is C, and I think it does say it in that paragraph down below, but C represents a phase shift, okay, which is a terminology that goes along with the periodic functions with horizontal shift. D is a vertical shift, which is the same thing that we've always called it. D is a vertical shift. But the phase shift, we haven't used that really before. It's just another word for horizontal. All right, some good things to remember. This is P for period. The period is 2 pi over B, and B then would be 2 pi over the period. That's going to help us in some of the problems that we have here, and really this should be the absolute value of B. But I think as long as you know that as you're doing it, you know that B has to be positive when finding the period. Period is a distance. So let's look at this next example here. We're going to construct a sinusoid of the period of pi over 5 and an amplitude of 6 that goes through 2, 0. Let's worry about the 2, 0 thing later. If it has a period of 2 pi, then we know that, or excuse me, a period of pi over 5, then we know that pi over 5, actually what I was going to write is this, that pi over 5 equal 2 pi over b, but let's go right to this one. B is going to equal 2 pi over the period. Period's pi over 5. So B then equals 2 pi times its reciprocal, 5 over pi, so B is 10. So we have the B value already. All right, we know if we, and then obviously the amplitude of 6 means that A is 6. Let's use those two things to piece together a function just with those two pieces of information. So 6, I'm going to use sine here. 6 sine of 10x. The reason why I'm using sine is I know sine goes through zero, zero, because it's a sine function. Sine functions go through 0, 0. Okay, so we know that, you know, if you wanted to do a little sketch of this thing here, or I'm not even sure when I set this thing up, if I wanted to start here, if that's what I meant this to be. But we have 0, 0 there, which would make this pi over 5 right here. And then, so that's 0. So this is the graph that we have there, that I have right here. So it would go from 0 to pi over 5, because that's the period. And then at pi over 10, it come back down through. At pi over 20 then, it would hit its maximum. And at 3 pi over 20, it would hit its minimum. That's just what I have graphed right there so far, or what I have written right there. We want this to go through the point 2, 0. Well, this is why I picked sine. I know sine goes through 0, 0. So if I can shift this whole graph right to that point that I just circled in blue is going to go through 2, 0 like I want it to. So how do we get it to shift over 2? Okay, let's just write it there. So if we shift right 2, will satisfy all 3 conditions. So far we've only satisfied 2 conditions, the amplitude and the period. So if we shift right 2, we'll satisfy all 3 given conditions. So how do you shift right 2? Well, we just said before, if we're going to go to the right, then we need to have x minus a value right there. We want to go to the right 2. So we're going to have x minus 2 in parentheses. That'll shift the whole function to the right. As long as we put the 10 on the outside, okay, and I'm going to put the 6 sign here, like that. So here's our function, y equals 6 sine times. So this is that'll give us the period of pi over 5, because b is 10, and this will shift us right 2. Now, if you want, you could distribute that 10 inside there, but I want you to see what that would look like. Okay, this does not mean it's going right 20 now. Okay, because in order to get that phase shift, you need to have B on the outside, which is why I just prefer this anyways. The only reason I'm showing you this is because your book may give you that as its answer. Oh, I'm missing my 6 right there, though, for the amplitude. All right, let's try one more like that here. Write 2 equations of the cosine function whose amplitude is 5 and whose period is 3. Pi over 3. So we're looking for a period of pi 3, an amplitude of 5. So it's going to go from 5 to negative 5. Okay, and so we're going to look at its cosine function. At its maximum halfway, and do something like that. So just a sketch of what they're asking us to come up with here. So really, all we need to do is find out what the b value is. B we know is going to be 2 pi over whatever the period is, pi over 3. So b is going to be 2 pi times 3 over pi, or 6. That's our b value. So if I treat this as my y value and my y-axis and x-axis, with this being the origin right here, that graph that we have graphed right there is y equals 5 times the cosine of 6x. They ask us to write, they ask us to write 2 equations that satisfy those conditions. Well, think about it. If we flip this function, I think this is the easiest way to do this. It would satisfy both conditions. Amplitude is still 5. Period is still pi over 3. How do we flip it? By putting a negative in front of it. So there are 2 equations that satisfy those conditions. We do have one more video to finish up section 4. It's not going to be nearly as long. We're going to go through a couple of the application problems that come in section 4 and talk about some of the transformations as well.